Let's have a look what we mean by a function and how we can represent functions. A function arises when one quantity depends on a second quantity. For each possible first value, we can only have one second value for a function. The first quantity is the independent variable. We usually use x for that. And the other quantity is the dependent variable. Very often y is used for that one. We can think of a function as a function machine where a number goes into the function machine and some number comes out of that function machine. Only one number comes out. A calculator is an example of a function machine. If we use the trig functions like sine and cosine, tangent, we put a number into the function machine, an angle, and some number comes out of that calculator. Only one number can come out for a function. How can we represent a function? Well, we can represent it in a table of values, we can represent it graphically, or we can represent it with an algebraic equation. Here's a table that shows the temperature during the day. This is displayed here as a table. We can also graph that information. A function can be represented algebraically with an equation. For example, a equals pi r squared is the area of a circle. Algebraic representations are often used and favoured because they are precise and we can work with them more easily than we can with tables or graphs. Function notation is used here where the dependent variable, the a, is expressed as a function of the independent variable, the r. We say that the area of a circle depends on r according to this relationship here. So we can write a of r is equal to pi r squared. Here's another example. F of x is equal to 3x squared plus 2x minus 3. The tax rates provide a good example of a discrete function. Between $0 and $18,200, you pay no tax. Once you get over that threshold, up to $37,000, you'll be paying 19 cents for each dollar that you earn over $18,200. Then you jump into the next tax scale where you're paying a higher rate, and there is also an amount that you're paying to start off with, which represents the 19 cents per dollar that you pay up to $37,000. And so on and so forth into the next bracket where you're paying an amount that represents all the tax you'd be paying up to the $80,000. And then 37 cents for each dollar over the 80,000 and right through to the highest tax rate there. We can write this algebraically where I is income and then the tax on the income can be written as this complex equation. 0 if you're earning less than 18,200. Between 18,201 and 37,000, you're paying 19 cents for each dollar over the 18,200. Then you skip over to the next bracket where you're paying the $3,572 and 32.5 cents for each dollar over the 37,000, and so on and so forth for the next two brackets as well. We can also represent that tax scale as a graph. You can see that the different brackets there have different gradients. As we go up, the gradients become steeper and steeper. Now, of the three representations, the table is probably the most useful one. A function returns only one value of y for each value of x, and this can be tested in a graph by drawing a vertical line. The vertical line represents one value of x, And if that line cuts the graph in one point only, as is the case in the first graph here, then we know we have a function. Similarly, in the second function, this value of x equals 1 here, is returning only one value of y. These two relations don't pass the vertical line test because the line cuts the graph in two places. So there are two values of y for one value of x. There's one up there and there's another one down below as well. That's also the case with the second graph there, where there are two values of y for one value of x. I'll now introduce the terms domain and range. All the possible values that x can have is called the domain, whereas all the possible values that y can have is called the range. And the domain and range are determined by the physical situation. In our taxation example, our income would have to be positive or zero, as is our tax. So our income is greater than or equal to 0, which can be written as 0 to infinity. That's called the interval notation. And we'll notice there that we've got a square bracket. It's not a misprint there. The square bracket means that the 0 is included, and the round bracket means that the that infinity is excluded. And the range, similarly, is that the taxation is also greater than or equal to 0, and we can stipulate that in the interval notation in the same way. Let's work out the domain and range for a few examples. In this function we have x squared plus 3. Now the x squared cannot be negative, and so when we add 3 we would have to have at least 3. So our range here is y is greater than or equal to 3, which can be written in that interval notation. X can take any value at all. We can put x equals whatever in there, and we can square it and add 3 to it. So the domain here is any real number. X can be any number. In our second example, we have y equals 1 over x minus 2. Now that denominator cannot be 0, so we can't have x equaling 2 there at all. So our domain is restricted. We can have any real number, R represents a set of real numbers, except 2, and that's how you read this notation here. And we can't make y 0. Doesn't matter how big we make that denominator, we'll approach 0, but we'll never get there. So y can be any value except 0. In our third example, we have y equals the square root of x plus 3 minus 5. Now the x plus 3 has to be positive, otherwise we can't take the square root of it. And so we have to have x greater than or equal to negative 3. Now the square root can have a minimum value of 0, and then when we subtract 5 from that, we will get minus 5 or more. And so the range is y is greater than or equal to minus 5. Next we'll talk about the continuity of a function. A function is continuous if it has no break. So it's the common meaning of the word continuous. Here's an example of a discontinuous function. This is the graph of y equals 1 on x. And you can see at x equals 0 there, the graph is discontinuous. Another example of a discontinuous function is this one here, where at x equals 2, we have a break there as well. So a function can be continuous over an interval. For example, y equals the square root of x plus 1 is continuous in that interval from minus 1 through to infinity. There are no breaks in that interval. A discrete function can take on only discrete values. In this example here, our y has only whole number values, -2, -1, 0, 1, 2, and 3. And you can see where the name step function comes from. That function, of course, is discontinuous. The absolute value function always returns a positive answer. The absolute value of -6 is 6. So we can see that the absolute value of x will always be x itself if x is positive, whereas it'll be the negative of x when x is negative, so that it returns a positive value. Here's the graph of the absolute value function. So you'll notice that y is always positive. When x is 2, for example, the absolute value is 2. When x is -2, its absolute value is also positive 2. We've seen that a function can only have one output for each of the input numbers. It can be represented in a table, as a graph, or as an equation. The function notation is quite useful, where it's saying that we have a function of some variable. The domain is the possible x values, whereas the range is the possible y values of the function. A function is discontinuous if it has a break. And a discrete function can take on discrete values only.